All right, I wanted to start with an activity for equilibrium today. And if you saw my post, I asked you to grab some objects, some coins, or some popcorn kernels, for example. The problem with popcorn kernels is they roll around. So I went to coins because they stay put. We need 24 to start with, and I think we will add another 8. And what I've done is made stacks of, all right, so if you can get 24 coins are good, or some kind of object. I'm making little stacks of 5 here. I've got 4 stacks of 5 and then my individual pennies flat. Let me write down a couple things. I'm going to look at a reaction. Slow, it's laggy. I'm going to write a reaction for A goes to B. Then we're going to say in the forward direction K1 equals 1/2 and K minus 1 equals 1/3. Okay, so if you can make a piece of paper like this, we've got side A and side B. Right now we're looking at reactants. And then we've got this little box of purgatory to move to B. So we're going to count them out. That's where we're going to stage them. And then at our reaction step, we're going to move them into B, and whatever's in B moves back into A. So we're going to simulate equilibrium. Then we're going to graph it. We're going to keep track of our concentrations down here. So if you can replicate on a piece of paper just the boxes, the little graph of A and B, it'll show up in a minute. I wonder why it's so laggy. What I want to do is get us all set up together to move together. So I'm kind of giving you a sec to get set up. We're going to simulate this equilibrium.
Okay.
And we have our rate constant K1 in the forward direction. And that depends on the concentration. The value of K does not depend on the concentration, but the amount of stuff that reacts depends on the concentration in the form of K1 times A. So I've got 24 pennies. And when I do step 1, we're all going to do this together. So we'll talk about it and then I'll say, okay, time 1. At that time step 1, 12 pennies are going to move to B, right? Because that's half of what we've got. We've got 24A. Half of them are going to move to B. So I'm going to grab 2 stacks of 5 and 2 individuals. And then now we're at time step 1. Boom. These guys go to B. I started with 24A, 0B, and now we're starting out our next time step with 12 and 12. Yeah, oh, I should probably do A goes to B here. K1 is 1/2. K minus 1 is 1/3. So now at our next time step, we're going to plan this out by saying, okay, half of A is going to move, so that's going to be 6 pennies, right? Half of 12 is 6, is going to move to B. Now, 1/3 of B are going to move back. And these are molecules, so you have to round down. There's no partial pennies. So let's see, we have 12 there. Oh, good, it's 1/3, so 4. So I'm going to break these guys up because they're no longer a stack of 5. 4 are going to move to A. Okay, boom, time step 2 happens. These go over here. These go over here. So recount. Now we're going to write how many we have. All right, ready for our next time step? Half of 10 is 5. Those are going to go to B. 1/3 of 14 rounded down. So 3 times 4 is 12, right? And then we don't have another 3. So that means we're going to have to move how many? 4, right? 4 times 3 is 12. We don't have another 4, right? Okay, then at that time step, these guys switch places. Here we've got 9. Is that right? And 15. Notice that the total pennies stays the same. Conservation of mass. Okay, next time step, half of 9 rounded down.
4.
And then half of 15 rounded down. Oh, sorry, it's not half, it's 1/3. 5, okay. Then time step happens and these guys swap places. And now we have 10 and 14. How will we know when equilibrium is reached?
Same on both sides.
So like here, after time step 1, we'd have the same number on both sides. Is that equilibrium?
It's when they're proceeding at the same rate, right?
Yeah. So how do we know when equilibrium is reached?
It keeps like oscillating between 9 and 15, 9 in A and 15 in B, and then 10 and 14 respectively to beyond the third time step.
Yeah, it's just going to go back and forth between those values. And we can see that because the amount of pennies in each step was the same. But what this is showing us is that we don't have enough pennies to actually represent the true balance that represents that equilibrium. So it's oscillating because we're only using 24 pennies. Does that make sense at all? Yeah, so it's a little bit of a harder case, but I feel like 24 is a good balance between what we can manage and how well it does. Okay, so we've reached equilibrium because why?
The forward rate and reverse rate are the same.
Okay, the rate forward equals the rate reverse, right? And that equals, in our case, that's going to be 1/2 times A equals 1/3 times B. What else? Are there other questions? How long does it take? It happened quickly. How do we know equilibrium was reached? And this is pretty well in the middle. These are pretty well balanced. So how do we know that we've reached equilibrium? Ultimately, the answer is going to be the concentrations are what? The concentrations are no longer changing in time. So we're going to look at that in a couple different ways. We'll look at it graphically. Now I want to simulate something else. So we've just got this snapshot. We've got 10 on one side, 14 on the other. I'm going to add 8 to side A. So here we've reached equilibrium. And now I'm going to disrupt that equilibrium by adding 8. So here, this is our disruption or perturbation, right? And I'm going to put 18 and 14. All right, so let me add another 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, and then we'll proceed. So the next time step, half of side A is going to move. That's 9, right? And then 1/3 of 14?
It's just 4 again?
Was 4, yeah. 4 times 3 is 12, and then there's 2 excess that don't get to react. All right, so time step, these guys move over, and we recount. 9 go. All right, so this is 32 total, and that should be 32 total. Okay, good. All right, next time step, half of 13, rounding down.
Is 6.
And then 1/3 of 19. Yeah, 6. All right. Then add our, 6 and 6. What's going to happen? So 19 and 13, has equilibrium been reached?
I think so.
Yeah, it's no longer changing in time.
Yeah.
What is the same about these, about this section and this section? What's similar, what's different?
Well, what's different is how many steps it took after the disruption to reach equilibrium. It was much shorter.
Well, this one just held a constant, right? So it turns out that 32 is divisible by both 1/2 and 1/3. So there's that oscillation, but this one took 2 steps to reach equilibrium. This took just 1.
Mm-hmm.
What about the balance? How much A and B? Thinking about this equation here, we can think about the amount of products over the reactants, and that's how we're going to be characterizing equilibrium. What does that equal? You rearranging this equation. Let's see, then I've got B on top, so I've got 1/3 over here. No, I got it wrong. I'm going to bring A down below. So it's 1/2 over 1/3 is 3 over 2, 1.5. So this is saying that the product side should be about 1.5 times the reactant side. That's pretty much true on the first part, and it's pretty true on the second part. So there we go. We just demonstrated the whole chapter. I like this demonstration because, and I especially like it with 162, because we can actually look at those values, and now we can refer back to it in terms of when we're talking about concentrations and it gets confusing. We can think back again to what did we put together now that we know about these rates. And we literally did this using the number of pennies for the A and B concentration. This is what we're going to define now as our equilibrium constant. Okay, so this is a lowercase k rate, is usually in italics, and it's lowercase. Our equilibrium constant is a capital K, and it is made up of rate constants. And K equilibrium gives us a quantitative measure of how much product there is compared to reactant. So we're going to work with these things and make them all more detailed. But that's basically everything that we're going to do in this chapter, kind of a big overview. Okay, I just opened up the lecture slides. I was thinking I would take a look at those. The chapter number is not accurate, but this is basically an overview of what we're going to do. We're going to, and the chapter sections again are different, but I'm sure I looked at it and it's in the same vague order. We have a little bit of extra stuff that we'll talk about. For one thing, oh, I don't see KSPs on here. So we're going to have equilibrium constants, a capital K, K equilibrium, or KC for the equilibrium constant with respect to concentration. And these apply to reversible reactions. And we'll be looking at the initial conditions of a reaction, like we started with all the 24 pennies on the A side, versus the equilibrium conditions once the concentrations are no longer changing. We'll talk about heterogeneous equilibria, which are involving aqueous gases and solids in different states. And then we'll take a look at how we can tell how far a reaction is from equilibrium with the Q, essentially. We will convert between concentrations and pressures. And then Le Chatelier's principle is about making a disruption to equilibrium and how equilibrium reestablishes itself. All right, and then problem solving. Quadratic equations, typically, and we'll use some approximate iterative methods, and we'll get some cool tricks in our pocket for solving those problems easily. Now, in our book, thermodynamic comes at the end, so I'm not sure how much we'll get into that this time. All right, so here is an example. Here is hydrogen and chlorine gas. In the presence of sunlight, they form HCl. So the light initiates that reaction, and it goes pretty much to completion, and it goes pretty fast. Here is nitrogen and hydrogen. So those can all hang out for a while at room temperature. And it goes pretty slowly, so slowly I clicked through because I was impatient. But it goes to completion. It takes a while, but they all react. Right? So it's a one-way reaction. However, if we heat the temperature up, 450 K, it goes much faster, but we have some reactants hanging around. So that tells us something about the reaction, how it depends on temperature and how long it takes, and the fact that the products are going to react back to the reactants. So we end up with reactants kicking around. So this is a two-way reaction. In our worksheets, we have a lot of the smog formation, colorless and brown kind of discussion. So we're going to define a reaction system as the conditions that it's taking place in. The concentration of everything that's there, the products and reactants, because they're all, if it's an equilibrium reaction, two-way reaction, they're typically all there at the same time. So that could include the pressure of gases if they're present and the temperature. So we have our reaction system, and then there's a position, given those conditions, there's a position of equilibrium that describes the system. So if we think about reactions going to products, the way it's written, however it's given, we have the left side and the right side. We have our rate forward is the K in the forward direction, those should be lowercase k's, times the concentration of reactants. The rate in the back direction is the K in the back direction, times the concentration of the products. When they're at equilibrium, those rates are equal, right? So that interconversion is perfectly matched. And that means that the concentrations are no longer changing. So here's the crabapple war. You got this apple tree, and you've got the annoying little boy throwing the apples over the fence, right? And the crotchety old man throwing the apples back. Now, the crotchety old man moves a little slower, so he's got a lot more apples, which means that he doesn't have far to go to pick them up. But he's just slower. So he's throwing them over. Now the annoying little boy's a lot faster, so he throws them back faster, so that K is higher on the little boy's side. But he doesn't have as many apples over there, so he has to run farther to get them. And so when they reach the equilibrium amount of apples, assuming nobody tires out, we're going to see that the old man's yard ends up with more apples in it typically. And the C's on this page are the concentrations. So usually molarities, but could be pressures, could be other measures of concentration. All right, so at some point, the rates are equal and the concentration, the number of apples on each side are no longer changing. And that's how we know we have reached equilibrium. So the ratio of those rate constants equals the ratio of the concentrations. And we saw that in our little activity a second ago. So they reach that equal ratio, and that's going to be our measure of when we've reached equilibrium and where that equilibrium lies. In our example, we will end up having the concentration of apples on the old man side is probably higher than the concentration on the boy's side, but they're constant. They're no longer changing in time. So it's easy to think about, if we say that they're constant, that it seems like they are equal. So we're not saying that they're equal. We're saying they're not changing in time. It's like we understand it 1 minute and then it's confusing it the next minute. Okay, so let's take a look at this graph. This is the reaction rate. And we talked about rates in the last chapter where in the forward rate, there's a high concentration and it slows down as the reactants disappear. And the reverse reaction starts at 0 if there's no products. But as you form products, that reaction rate gets faster. At some point, the rates become equal in the forward and reverse direction. And that's one way to see that you're equilibrium. So they reach equilibrium at this when the rates become equal in the forward and reverse direction. Now, in terms of the concentrations, they are not equal concentrations, but they do reach a concentration that's no longer changing in time. So they do flatline. In this example, do I have an equation there? This would be for that H2 plus N2 reaches ammonia reaction.
Okay.
At elevated temperature, we have a ratio of these concentrations. There's more hydrogen than ammonia and nitrogen, but they're no longer changing in time, right? They reach a constant concentration, but this is a dynamic equilibrium, which means that the reactions are still going forward and backwards. The individual molecules are still undergoing reaction. It's just that the rate of reactions and the overall concentrations are no longer changing in time. Okay, so the reaction's still occurring. It's just balanced forward and backward.
So that, like in terms of the penny example, that was where we got to the point where we were just switching back and forth the same number of pennies each time step.
Yeah, exactly.
Yeah.
So we got to 6 pennies and 6 pennies. They weren't exactly the same pennies, but the total number of pennies was going to be constant.
Right.
At that point. All right, so that is the equilibrium constant for our generalized reaction, where we have our coefficients as the lowercase and the chemicals as the capital letters. We would write our equilibrium constant like this. Basically, I summarize it in my mind as products over reactants, where it's the concentration of each product raised to the coefficient times all of the products raised to their coefficients divided by all of the reactants raised to their coefficients. The thing about the equilibrium constant is it's a constant. So at a given temperature, it does depend on temperature. At a given temperature, though, that ratio is not going to change. So even when we added the extra 8 pennies, we still achieved essentially the same constant, the same equilibrium constant. And in our case, it was about 1.5. So for this reaction, this is a nice simple one, right? Just one reactant, one product. And we can see that those concentrations become constant in time, but not necessarily equal. We can start with only reactants present, or in the second picture on the right, we can start with only products present and watch it go the other direction. Right, so on the right side, this is starting with just NO2 present, and then the NO2 decreases as the N2O4 increases. Now, as long as the total amount of stuff, the total mass of nitrogen, for example, is the same, equilibrium concentrations come out to be the same. Doesn't matter which side the equilibrium starts at, that ratio for the given reaction system will be constant. So it's just another way of saying that ratio is constant. All right, so, and again, these are the reaction rates. So it's really important to notice what is being graphed. So that's a helpful way to see what's going on. Okay, so the initial concentrations, we could start with all reactants and no products, and we get that equilibrium constant. We could start with all products and no reactants. And again, we get that same equilibrium constant, right? The same concentrations. Now notice in run 3, we have a different amount of initial reactants. And those concentrations are different because there's a different amount of stuff. However, the constant is pretty much the same. We see a little bit of variance in that second decimal place. And then we start all the way at products again. Different concentrations, same equilibrium constant. So really emphasizing that constant part. Okay, what else do we need to do here? Just building these. So Yeah, we can talk about the position of equilibrium. We can say for this reaction, it tends to lie towards the right if it was towards products, or towards the left if there were more reactants. So we can say where the position of equilibrium lies, which one has the higher relative concentration, by looking at the size of K. If K is large, then which side should it lie on? You can give that equation. Here it is. So if K is large, that means there's a lot of products and not many reactants left. So for example, in our typical one-way reactions, K is huge. If we have a small K, then that reaction doesn't go very far to the right. It mostly stays as reactants. So you may have seen this in the case of like weak acids, where they stay together as the neutral molecule, usually about 10,000 molecules for every one that breaks into the ions. Yeah, 10,000 is relatively small. That's going to be our cutoff for small. Okay, so in a picture like this, we're looking at mostly products. And notice that we form 2 HBr, so that concentration is squared when we calculate the value of K. That's going to be large. We can see from the image at equilibrium, it's mostly products. Just one hydrogen, one bromine. For N2 and O2 going to NO, we see what, 1, 2 NO molecules, and the rest are all reactants. And so that means that it lies mostly to the left, and K is a very small number, right? So small amount of products, large amount of reactants. Okay, and then I think we get into calculations. So for those, I want to go back over to our worksheets. The example we start with here is for water at different temperatures. Now this always drives me crazy. Why do I have this in Fahrenheit? It's just to be tricky. So I'm going to write those in degrees C. Here we're looking at melting, right? We're looking at the solid ice melting to form water, so very intuitive process. This occurs at what temperatures?
1 degree Celsius?
Yeah, so temperatures greater than 0 degrees C, right?
Yeah.
So like 25 degrees C, our nice warm room, definitely going to melt the ice. All right, if we have a glass filled with ice cubes and we add some water, are we going to have any of the water freezing into ice? Okay, so we've got our ice cubes in there, and then we fill it up with water. The thing is, we've got all this heat in the environment, right? So typically this is going to proceed spontaneously towards water as a liquid because of all that heat in the room. So let's take the same kind of system. We'll just make an ice slurry. We have ice and water, lots of ice, just filled with water. And then we're going to cover those. And we're going to place them in these 3 temperatures. Okay, 38 degrees Fahrenheit is about, what's that, 4 degrees C? Most fridges are set to be 4. Then 0 degrees Fahrenheit is, most refrigerators cycle. They have a thermostat that cycles. So it would be hard to freeze it solid unless it was below freezing, right? It would have to be pulling the heat out and keep it consistently below the freezing point. Is at 0 degrees C. This one's probably going to be the mixture, right? Depending on where it's cycling. If it's truly held at 0, it might turn to ice.
Mm-hmm.
Okay, sorry about that. We won't always have reactions going one way. If it goes essentially to completion, then we have just products, right? So that would lie to the right. If it only a little bit reacts to products, then that would lie to the left, so towards reactants. And then some are pretty balanced. You end up with products and reactants both there. Then you have everything in solution at once. So this is an acid-base reaction. Thinking about our indicators. So what happens there? Some values here. So a little bit of a review of limiting reactants. Remember this applied in the acid-base reaction. You calculated the heat in the calorimetry lab. You did an acid-base reaction, and you had to figure out how much water actually reacted based on the limiting reactant. And I like to do my values here. This will be our limiting reactant. And our sodium hydroxide is in excess. Do you know how to calculate the excess? So this is 10 millimoles. This is going to be subtracting off that 10 millimoles. 0.5 millimoles left. And then that is going to be in a new total volume. Right, so NaOH final is 0.5 millimoles over 20.50 milliliters. Right, so just quick stoichiometry review in case the Alex wasn't enough. You can just do these in millimoles and milliliters. The millis cancel. All right, using phenolphthalein, how do we know it's a one-way reaction? Phenolphthalein is an indicator, so at low pH, it's what color?
It's clear, right? Or
clear. Yeah, and then it turns pink at like 8.5 or 9, so right in that steep upward part. pH, it turns pink. And so we know that the pH stays high. So that excess sodium hydroxide sets the pH. All right, how about eggshells? Decomposition of eggshells, calcium carbonate. So to what extent does that reaction occur?
very slowly?
Yeah, it's very, very slowly. Sometimes this one's a demo we use too. Cobalt +2 complex. Then the reactant side, it's pink. And the product side, it's blue. And I'll probably find some videos using this one. They're all over. Okay. And at equilibrium, the mixture is purple. So what does that tell us? Well, it tells us that that both reactants and products are present at the end. So we'll stop there. Let's see. So I have the lab assignment up for you. And I'll stay on Zoom so you can check out that data. Let me know if you have any problems or questions about it. And if you want to work through it, I added more tables. I added another Excel file with formatted tables according to the way the results request, that 16 row table, all nicely formatted for you. And so there's just a quick question in there for the lab data to get that data. And then you can begin working on that if you want to do it today in our lab time. Since you don't have to do any of the procedure, that might be an efficient way to use your time. And I'll be here online to answer questions.
Okay, so that's it? Do we have to stay here during the lab time or no?
Only if you have questions. You don't have to stay in the lab time if you want to just work on your own.
All right. Thank you.
Okay, cool.
Professor, so for everything, you should notebook?
I would put, so there's a couple different things. Yes, so all of your scratch work relating to lab should be in the notebook in the appropriate section. And if you've made those data tables out in advance, I don't think they're given to you until I just posted them, but constructing those data tables is actually a pretty difficult task. It really helps show where you know what the experiment's supposed to do and where it doesn't. And so I found that when I had to construct my own data tables, I'd come into lab and I'd be like, oh, okay, I didn't lay it out very well. So that's actually the question I asked is like, what do your data tables look like in comparison to these ones that I just did images? So you have to be careful. One of those sets of data was constructed in a table that was inverted. Yeah, just it's helpful if you have a place to put your data in your notebook and all of your scratch work in there that you need. You should always end with words, but since I want you to submit a typed report, you don't have to first write it out. You could type it and then include it in there, for example.
And so we'll pretty much just follow the lab manual for
Yes.
For this. Would you be able to take a look at drafts maybe before the final?
Yeah,
lab report?
maybe one draft per
Okay.
person.